Hello everyone, my name is Thomas Ramos from the Spanish Research Council in Madrid, and today we'll present to you some recent results we put in archive together with the Juanjo Garcia report and Ming Li. It is about a scheme to generate multi-photon states by synchronizing many single-photon sources using a cavity. Well, when doing scalable quantum information processing with photons, one typically thinks on a large photonic circuit with many photonic inputs, and then these photons are transformed with many beam splitters, phase shifters, and so on. And at the end, with many detectors, these are detected and retrieve the quantum information. There are many challenges to solve before reaching this ambitious goal. And one of them is to prepare a large scale state of indistinguishable photons with exactly one Fock state per channel. This is the aim of my talk. The state of the art in this respect is a boson sampling experiment with 14 photons done in the Pan group in China. Here, a quantum dot emits a train of photons, and these photons are routed on different channels via the multiplexer circuit and then synchronized by delay lines. This works, but the efficiency is very limited, so they could get a 14 photon coincidence with a rate of millihertz and a probability of 10 to the minus 11, and it's hard to scale this much further. So having this in mind, we thought of a circuit implementation of a multi-photon source for microwave photons. The implementation can look naive at the first glance, but actually it is very efficient at the end, and I will explain the following. We require n transmons, and each transmon will represent a single photon source. All these emitters are coupled to a common transmission line cavity with same coupling, and in addition, we require one independent channel per emitter to collect the photons after emission. The cavity is very important for the driving technique we use that we call cavity-mediated synchronization. This is that we require a strong driving on the cavity to build a large coherent state in the cavity, and there will be a small quantum fluctuation around it. But when doing this displacement transformation, one can show that the net effect of having the drive on the cavity will be to have a driving on all qubits, and this driving will be completely synchronized. So at the same time with this cavity-mediated driving strength G times alpha. So driving only the cavity, one can drive all emitters at the same time. The advantages of this approach and doing it with circuit D is first that these independent channels to collect the photons are very natural to implement compared to nanophotonics, for instance. And the efficiencies to collect the photons is really high. It has been shown already in experiments of 99% or larger. And also, one can use flux-tunable transmons to have them almost with equal frequency, and thus to prepare nearly indistinguishable photons. The main limitation of our setup is cavity-mediated interaction between emitters. But this can be suppressed by being in the bad cavity limit of weak coupling, and where this interaction will scale in G squared over kappa and also the collective decay. Therefore, the regime of operation of our scheme is the following. First, we want this cavity-mediated driving of G times alpha much larger than anything else to prepare to make a pi pulse and prepare all qubits synchronously in the excited state. Then a bit lower will be the decay into the waveguides, such that after they are excited, they will each emitter will decay independently into the wave and emit one photon. And all the unwanted effects like the cavity-mediated interactions, super radiance, and the decoherence like dephasing and losses here in the output should be much more than this to avoid these defects in the preparation of the state. And this way, we can prepare this state of product of uncorrelated photons. Well, having this separation of timescales is actually realistic with state-of-the-art technology in circuit D. First, we want a large cavity occupation on the order 10 to the 4, and this is can be done by having a very large driving on the cavity, which could look 40 GHz very, very large, but actually is realistic. And in experiments, I have already seen 10 to the 5 or 10 to the 9 photons in the cavity, which is really the limitation, not the driving strength. We also assume a weak coupling between emitter and cavity, such that these cavity-mediated couplings are very small, and the cavity-mediated driving is like 6 orders of magnitude larger than that. And regarding the coherence, we consider different parameter sets, but I will concentrate on the ones already available by IBM Quantum Computer here. And the important is that we take the gamma, the decay that we want into the waveguide, much larger than this, such that we can fulfill this inequality. And here I show a typical dynamics for a synchronized emission of 2 photons. For instance, we first drive strongly the cavity, build this coherent state, and this will induce synchronized pi pulse over the emitters and put them both on the excited state. And then after the excited state, we turn off the cavity and the emitters decay exponentially independently on each channel, and the probability of emitting 2 photons, 1 per channel, goes to 1, and specifically 98% for these parameters, and the other is also similar. So in this last slide, I want to discuss the scalability of this approach when increasing the number of emitters. We did a calculation with quantum trajectories to calculate the PN, which is the probability of emitting n photons exactly on independent waveguides at the same time. And we see that up to 12 emitters, what we could calculate, this within the error, this matches very well with the limit of having exactly perfectly synchronized n photon emitters, which will be an exponential decay with the probability of emitting 1 photon on each channel. So we see that therefore the single photon sources are really well synchronized and independent in our scheme, and also the efficiency is very large. If we could have 30, we could reach 85% efficiency of emitting 30 photons. To see if we can really trust this extrapolation, what we did is to calculate the difference between the actual probability of emitting n photons on different channels and the ideal case of n independent emissions on the independent channels. And we see that this n photon dependence is really small for the parameters we take, that on the order of 10 to the minus 4, even for 30 emitters. And we see that the behavior here can be well explained by a quadratic function in n, and with a prefactor that is really very, very small on 10 to the minus 11, 10 to the minus 7. So this means that, as we show in the paper here in detail, we can extrapolate this behavior as long as the dn, this photon dependence, is much more than 1, which for these parameters is easily obtained for 100 photons and even more, 100 emitters. So extrapolating this to 100 photons, this same behavior, this means having a probability of emitting 100 photons at a time of 30%, and having repeating this with a decay rate of 300 kilohertz, which we'll be achieving for the parameters we consider, we can achieve a rate of emitting 100 photons of 100 kilohertz, which is really many orders of magnitude larger respect to the millihertz result of the pan group. So it's a huge improvement over that. As conclusions, I want to say that I show a scheme for efficient multiphoton generation up to 100 photons. This can be done in a realistic implementation with state-of-the-art circuitry technology, and this scheme is also resilient to inhomogeneities, as we show in the paper here. For example, inhomogeneities in the frequency of the qubit, or the couplings to the cavity and so on, up to a certain extent. That is also realistic. So an outlook of this is that this scheme could enable quantum advanced experiment with 100 microwave photons, for instance, boson sampling with many photons. And our future plans is to also include now interaction between the emitters and with time dependencies to create in a scalable way entangled multiphoton states, for example, cluster states. These are our ideas. Thank you very much for your attention.